So hey guys, welcome to ThinkX Academy. In this tutorial we are going to study about the combinational circuits. So basically combinational circuits are those circuits which are made by arranging the logic gates. So in the previous tutorial we have already discussed about logic gates. So in this tutorial we are going to make use of those logic gates and we are going to make combinational circuits, and they are actually used to perform a lot of very useful operations. So let's start with the first combinational circuit that we are going to discuss in this tutorial. So the first combinational circuit that we are going to discuss is the half adder. So in this tutorial we are going to learn how these circuits, how the half adder, which is basically a combinational circuit, how it is used to add two numbers, right? So we are going to make use of the logic gates obviously to make the combinational circuit, and we're going to make a half adder which will implement the very basic addition of two numbers. So let's start with this. So let me give you a very simple problem. Let's suppose we have two numbers. So we have two numbers 7 and 2. So now we want to perform addition. So we know when we perform addition it will be 9. So application programmers can very simply do this implementation, but they don't know how this whole thing is working because our computer does not know 7, 2 or 9. So our computer works only in the binary language. So binary language is a language which makes use of zeros and ones. So basically a low voltage is represented as 0, and whenever the computer gets a high voltage signal, that means it is a 1. So computers work on ones and zeros. So what we have to do is we will have to do something to convert these numbers, and these numbers are basically represented in the decimal format. So we will have to convert it into zeros and ones, or simply we will have to convert them in the binary format so that our computer can now perform some operations onto it. So let's see how we can convert them into these binary numbers. So basically at the system level there are decoders which are used to convert them into the binary format, and similarly we have more useful circuits which can also do the reverse thing, but we are not going to study about them, how they actually work, how they actually convert these decimal numbers into the binary format. So in this tutorial what we will do is we are going to convert them into binary numbers. So let's convert 7 into binary format. To convert any number into the binary format we have a very simple procedure. What you will simply have to do is you will first have to just write 2 raised to the power 0, 2 raised to the power 1, 2, 3, 4 and so on. So initially we are going to initialize all of them as 0. So we know the value of 2 raised to the power 0 is equals to 1, 2 raised to the power 1 is equals to 2, 2 raised to the power 2 is equals to 4, and similarly 8 and 16. So since we are using binary numbers we are going to use 2 raised to the power 0, 1, 2, 3, 4 etc. So initially we will assign all of them as 0, and now we will have to make a combination of these so that if you will add these results you will get the desired number. So you can see that if I will add 4, 2 and 1 I will get 7. So in order to do this, what we'll have to do is we will just have to make these positions as 1. So we are making use of 2 raised to the power 0. So we are going to write 1 here, 2 raised to the power 1. So it will also be 1, and similarly 2 raised to the power 2. So this will also be 1. So if you want to convert any binary number, so you can see that this is a binary format. So if you want to convert it into this format again, what you will simply have to do is you will just have to add these respective positions. So it's a very simple task to do. So in this manner we can actually convert any number to a binary format. So why are we doing this? We are doing this because our computer can read only binary numbers. And since we are making use of half adder, it basically converts, it is used to add the bits, right? So half adder is used for addition of bits, that is 0/1. So first of all, we will have to see how these numbers are actually converted into binary format, and then we are going to pass these as an input to the half adder, and we will see how the addition really goes on, right? So the next number is 2. So let's convert 2 into the binary format. For that, I know that I will have to choose this one. So 2 raised to the power 1. So under this I will write 1, and rest of them will be 0. So now instead of passing 7 plus 2 to the computer, I'm going to ignore these zeros. So 1 1 1 plus 0 1 0. So instead of passing these numbers are actually converted into the binary format, and then we will perform the binary addition. You can see that we will have to add this bit with this bit. So this is 1, this is 0. Then similarly we will add these 2 bits and then these 2 bits. And this is not basically the mathematical addition. We are going to perform we are going to implement the half adder to implement this. So in order to perform addition of these bits, we are going to make use of half adder, right? So before creating the circuit of half adder, I just want to convert 9 also into the binary format. So in order to convert 9 into the binary format, I will use 8 and 1. So 2 raised to the power 3 is 1, 2 raised to the power 2 will be 0, 2 raised to the power 1 will be 0, and 1, and similarly 0. So when you are going to add these numbers, you are going to get 1 0 0 1 and 0. You can see that this is the 2 raised to the power 0, 1, 2. Alright, so this should be 1. This is 2 raised to the power 3. So 9 is represented as 1 0 1 0. So you can see that how we are going to perform this addition. You can see that 1 plus 0 is giving us 0. 1 plus 1 is giving us 1, and similarly it goes like this, right? So we will have to perform some operation which we are going to use this half adder, which is basically a circuit and a combination it is a combination of exclusive OR and gate. So you can see that so this should be also 0, and 2 raised to the power 0 should be 1. So you will have to be very careful while representing it in binary format, because if you will overwrite some wrong place, you will get the wrong result. So I will write 1 0 0 1. right? So if I create a exclusive OR gate, so I know the representation is like this. So let's say that this one is the A and this one is the bit B. So now what I'm going to do here is I'm going to pass A and B to this exclusive OR gate. Then I'm going to get an output X. So we know that in case of exclusive OR, we are just going to consider odd number of ones. So if we are having odd number of ones, then the answer will be 1. Right? So what I'm going to do here is I'm going to draw a truth table, and since this is sum, I'm going to represent it with S. So here in the truth table, what I will just do is, since there are 2 bits, I'm going to write all the possible combinations. So these are all the possible combinations, and here is the S. So now I will have to perform the exclusive OR operation between A and B. So it will look like this. So it can be expanded as A B dash plus A dash B, or simply just you can use this odd numbers of 1 theory, right? So in the first case, in this case, you can see that there are no ones, so that means the number of ones is 0, which is an even number, so I'm going to write here 0. Here you can see that it is odd numbers, so I'm going to write here 1, and similarly 1 here, and here you can see that we have even numbers, so I'm going to write 0 here. So this is how you can add 2 inputs. So if you see here, so 1 and 0, these are the 2 input values. So 1 plus 0 will be equal to 1, as you can see in this truth table. Similarly, 1 plus 1 is equals to 0. So you can see that it is 0 here. Similarly, 1 plus 0 is 1. And now what we are going to do is, you can see that we are now going to convert this. This is the desired result. Alright, so we know that 1 plus 0 gives us 1 from this truth table, and 1 plus 1 will give us 0, and 1 plus 0 will give us 1, but you can see here, instead of giving 1, I have written 10 here, and I've written 10 here because we want this desired result. So why is this error occurring here? So I want to show you, which is also our next output, which is the carry. So I want to explain you what carry signal is. So let's take an example like this. So if we want to add 7 plus 4, so we will add 7 plus 4, and this will give us the output as 11. So I know that 1 will be here, and 1 of 11 will go up, and this is basically known as carry. So when I will add these, I will get 1 here. Similarly, in this case also, when you will get 2 ones, as you can see here, there are 2 ones, you cannot write it just 0, because 1 plus 1 in the binary language will give you 1 0. So how does it give you this number? You can see that if you convert this into binary format, it is basically 1, it is also 1, and if you will add them, you will get 2. And we know that this is representing, this number is also representing 2. So 1 plus 1 will give us 0 and a carry of 1. So we need to maintain a signal which will hold this carry value, because if we are not going to hold this carry value, which is this one, our whole output, our whole desired result will get wrong. So you can see that how I've explained this. if you will add 1 plus 1, it will give you 1 0. To convert 1 into the decimal format, I will just make use of this. So it will be 1 in the decimal format and 1 in the decimal format. So if I will perform the addition using the decimal format, it will give me 2. So if I want to convert 2 into the binary number, I can do this. You can see that 2 will be here. So this will be 0 and this will be 1 and rest of them are 0. So it will give me 10. So from the exclusive OR gate, we are getting 0, but we are not getting this 1. So this means that I will have to create some signal which will hold this value 1. And this will happen only in case when both the signals are 1. So when both the signals are 1, our carry will be 1. So we are also going to use the AND gate, and basically AND gate is used to provide the carry signal. And as you can see from here that 1 plus 1 gives you 10. So this 0, so I will write it like this. So this 0, we can obtain it from the XOR or the exclusive OR gate, and we can obtain 1, which is the carry signal, by using the AND gate. So we know that in the AND gate 1 will give us 1, and if there is any number of zeros, we are going to write it like this. So this is the sum and this is the carry, right? So what we are going to use is this is the half adder, and half adder make use of exclusive OR and the AND gate to perform these operations. And you can use this table to add any two numbers, and if you want to add one bit with another bit, you can make use of this truth table. So let me just draw the half adder circuit and how it looks like. So I've just given an explanation of why we are using the exclusive OR AND gate, because I will have to first just show you how addition works and how we convert and why there is a need to convert it into the binary format. Then only we could have understood what exactly is a half adder that is used to add bits. So in order to add any number, we convert it into the binary format, and then we add them bits by bits. To add them bits by bits, we will use of the half adder, which uses exclusive OR gate and the AND gate. AND gate is used for the carry signal and exclusive OR is used to get the sum signal. So in case of 1 and 1, we have seen how we need to maintain a carry signal. So let me just draw a circuit diagram of the half adder using the exclusive OR and AND gate. So I'm going to draw it here. So we have two signals, which is A and B. So these are the two input signals which can have any value 0 or 1, 0 or 1. So we are going to give these two inputs to the exclusive OR gate, and this exclusive OR gate will give us the signal S, which is the sum, and then we are going to pass these two signals again. We are going to use the AND gate to get the carry signal, and I have already shown you what is the use of carry signal. So if I will just write it like this, this is carry signal and this is the sum. So this is 0 0, 0 1, 0 1 and 1 0 in case of these combinations. So you can see here that if I want to add these two numbers, the result will be 0. The result will be this. And if I want to add 1 plus 0, the answer will be this. If I want to add 0 plus 1, the answer will be this, and if I want to add 1 plus 1, I will get the answer 1 0. And if you convert them into the binary numbers, into the decimal system, you will be able to get the right sum. So this is basically the use of half adder, and this is the circuit diagram, and this is the truth table, and I have already shown you an important concept of carry signal. In the next tutorial we are going to use full adder, and basically it is known as full adder because it makes use of two half adders. So we are going to use two half adders to implement the full adder, and basically full adder is used if you have three input signals. One is the A, second one is the B, and the third one is the carry signal of the input. So this is the carry signal from the output. So we will study about carry signal input, which is represented as C of I, in the next tutorial, and we will study about the truth table also. So that's for it in this tutorial. Please like and subscribe our channel. Thanks for watching.